Alright guys, welcome back to another quantum mechanics lecture. And in this lecture we're going to discuss quantum numbers for electrons. So that's going to be the basic concept and theory that we're talking about in this lecture. And I do want to warn you that this can be a bit confusing when you first learn it, but as soon as you get a hold of it, and we'll practice a little bit towards the end of this, as soon as you get a hold of it, the concept's going to become easy. So let's go ahead and get started. So the first thing I want to talk about is what are quantum numbers. Quantum numbers are a set of designated parameters that are used to identify electrons and the orbitals that those electrons occupy. So they're almost like addresses or fingerprints that will identify individual electrons, if you will. And just like a fingerprint or an address, a quantum number is unique in that no two electrons in the same atom can have the same set of quantum numbers. So two electrons might have a very similar set, but they're going to differ in at least one or more of the values within that quantum number set. So let's take a look at each of the quantum numbers and what they actually represent. So here we have the quantum numbers. The first quantum number is referred to as the principal quantum number. And the principal quantum number we designate as lowercase n. You can see I have on the slide there. And n, lowercase n, is going to refer to the energy level or the valence shell level in which the electron resides. So when we say 1s2, 2s2, 2p6, etc., when we're talking about those individual levels, the 1 and the 2, those numbers coming before the shell itself are the quantum numbers. So when I say 1s, the principal quantum number is 1. If I say 2s and 2p, the principal quantum number is 2. 3s, 3p, and 3d, the principal quantum number would be 3, etc. So when we are going through and looking at that first number coming before the shell itself, that's the principal quantum number. And it represents the valence shell that we're currently in when we're looking at an electron. So next is the angular momentum quantum number. And this is going to designate the actual orbital that we're looking at. And it's designated with a lowercase l when we represent it. So L is going to describe the type and the shape of the orbital that the electron resides in. So for instance, we can have an S shell, a P shell, a D shell, or an F shell. And the value of L is going to tell us which one of those shells that we would be in. So the next one that we have is the magnetic quantum number, which is referred to as M sub L. And M sub L refers to the orientation of a given orbital. So sometimes we refer to these in our lectures or in class as suborbitals. What's really happening, for instance, with P, when we talk about the suborbitals in P, you really have 3 P orbitals, but they have different orientations. So you have a P orbital in the X direction, a P orbital in the Y direction, and then a P orbital in the Z direction. And the direction or the orientation of these orbitals or suborbitals, as we sometimes call them, is going to be found with the M sub L quantum number. And then finally we have the M sub S quantum number, and M sub S is referring to the directional spin of an electron. Now this is not the spin around an orbital itself. That would be L when we're talking about the actual orbital that the electron spins around, the angular momentum. Within each electron, it spins on its own axis, just like the Earth does. So we have the Earth rotating around the Sun. That's kind of like an electron rotating around the nucleus in its outer shell. And then the electrons themselves have individual spins, just like the Earth can spin on its axis. And those spins are represented by M sub S. So now that we have defined each of these quantum numbers, let's go ahead and take a look at the limits that we're going to place on each quantum number, because each quantum number is going to have certain parameters or limits that we cannot exceed. So for the limits, let's start with n and we'll work our way down. For n can have any whole number integer starting with 1 and then moving up the scale. So we can have 1, 2, 3, etc. You could have 4, 5. At some point, you're going to start cutting it off around 6 or 7 because the periodic table doesn't extend past that. and most of the atoms that go down far into those levels are going to start to become relatively unstable, and there's a lot of radioactive decay and things like that. But technically, this could go as high as we wanted. So that would be for n. L can be up to n minus 1. So I need to clarify what this means because a lot of times students get confused. That does not mean that L is only equal to n minus 1. The limit is up to n minus 1. So it's important to note that n minus 1 is a limit for L, but not the only value that L can be. So remember that L is the description of an orbital itself. So we define an L of 0 as an s orbital. You can see this over here to the right. Okay? If my L is equal to 0, then I have an s orbital that I'm referring to. If my L is equal to 1, I'm talking about a p orbital. If my L is equal to 2, I'm talking about a d orbital. And then finally, if my L got all the way up to a 3, I would be talking about an f orbital that the electrons would be occupying. So next we have m sub L. We were discussing that as the orientation, sometimes called the suborbitals. And these values can occupy an entire range of negative L to positive L, including the value 0. And those are going to be whole integers. So for instance, if I had a d orbital, my L would equal 2, and therefore my m sub L could be negative 2, negative 1, 0, 1, and 2. It's going to be the integers ranging from the negative values to the positive. So you should also note that if you have s, which is 0 itself, then then m sub L is going to have to be 0 as well, because there is no negative and positive 0. So anytime that L is 0, m sub L must also be 0. That's the only option it has. Now once I go to a p orbital, I start having those suborbitals and side orientations that I wouldn't have with s. So once I get to a p orbital, I can take negative L to positive L, and if p is equal to 1, that's negative 1, 0, and 1. And those three individual m sub L's represent the three orientations that I could have for a p orbital. And again, we'll practice some of this in the following slides so that it makes sense. And then finally we have m sub s. This is sort of the easiest one. M sub s is the spin, and the spin can only have a plus 1/2 or a negative 1/2 spin value. And we do not have 0 spins. That would imply the electron isn't spinning. And it's plus 1/2 and minus 1/2 are the values that we associate with the spin. So we're not going to have any other type of spin values. So I want to bring up the periodic table here so that we can look at it for a second. If you take a look at this periodic table, let's look at where the n quantum numbers would be found. They would be found along the side, and a lot of periodic tables show this along the side here. 1, 2, 3, 4, going down, etc. as you go down the table. So as we go across this, hydrogen and helium would occupy n equals 1. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon would represent the n equals 2 level. Sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon would represent the n equals 3 level. So I think you get the idea. As we're going across, we're representing the level that we're in. Now remember, the D shell is going to be one level behind the quantum level you're in. So when I start out with that first D shell, that is actually 3D, even though it's right next to the 4s shell. So you want to keep that in mind when you're assigning these quantum numbers. So that would be the n. Over on the left-hand side of the table, right here that I'm circling, this is the s shell. So that would be the L equals 0 value. And then I'm going to circle over here minus helium, because helium is in the 1s shell. What I circled right there, that's the p block that we're referring to. And so when we're in a p orbital, we're talking about a L equals 1. I just circled the d orbitals, which are in the middle here, referred to as the transition metals. And that is my L equals 2, and then my L equals 3. If you come down and you look at the lanthanide series down here, this would be the L equals 3, and that's the F shells that we have there. Now within each of these, we have subshells except for the S. So each orientation or subshell can hold 2 electrons. So here, the S shell only has 2 electrons in each quantum level that I'm circling. And so you don't really have an M sub L other than 0. But once we go up to P, we know that L equals 1, so M sub L can equal -1, 0, and +1. And we break up the shell in quarters of 2. So we say right here, that would be -1, this would be 0, and this would be +1. And you can see that in every single period that we have here. We can break these up into 3 suborbitals, each of which hold 2 electrons. And for the D, if you look here, here's 1, 2, 3, 4, 5. And so this would be, because L is 2 for D, -2, -1, 0, 1, and 2. So if this is still a little confusing, we'll go ahead and we will draw these out. We're going to do it for the S, the P, and the D. Hopefully you should get it, and you could continue on with F if you need it. So let's take a look at the S orbital. For an S orbital, we only have one of these suborbitals. So I can pick out any value of n. Let's go ahead and say let's do for the 1s, the 2s, and the 3s. All right, so we'll continue and do a couple of these. So for a 1s shell, n would have to equal 1. The L would equal 0 because I'm talking about an S shell. The M sub L would be equal to 0 as well because it can range from -L to +L. 0 doesn't have positives and negatives, it's just 0. And then we have M sub S, and that would refer to the spin. We typically designate a +1/2 spin first, but you could put a -1/2 spin as well. Every single orbital will have a +1/2 spin and a -1/2 spin when we deal with them. So 2s would be n equals 2. I would still have L equals 0 because it's an s orbital. M sub L would equal 0. And then M sub s could equal +1/2 or -1/2. And same thing here. N would equal 3. L would equal 0. M sub L would equal 0. And then M sub s would equal +1/2 or -1/2. So I think you guys hopefully get the idea for the s orbital here. So let's turn around and take a look at our p orbitals. So when we normally deal with a p orbital, we're dealing with 3 of these orbitals, which can hold a total of 6 electrons. So again, depending on what p I'm referring to, I could have 2p, 3p, etc. I'm going to have n equals 2. I'm going to have n equals 3 here. Now, the L value when I'm dealing with the p orbital is 1. So my L is equal to 1. Okay? And then my M sub L is going to depend on which orbital I'm in. So this one would be -1. This one would be 0, and this one would be 1. So I could be in any of those. So let's say that I'm interested in this electron right here. I would say that I'm in M sub L of 0, and then I would say I have an M sub S equal to, this is a positive spin when it's up like this, so +1/2. So let's pick out another one. Let's say I'm interested in this electron right here, and we'll say it's in the 3rd level. N equals 3, L equals 1, M sub L is equal to, and now here I'm going to pick out the -1 because I'm interested in this electron up here. So -1, and then my M sub S, if I look, this electron is spin down, so I'm referring to the -1/2 electron. Now you can see that no 2 are going to hold the same value. If I circle this electron and want to do that, let's say it's also in the 3p. We would say n equals 3, that's the same. L equals 1, that's the same. It's still in the sub -1 orbital, so -1. But then when we get to the MS, this guy has a +1/2 spin, And so my quantum numbers differ at this point. And so I think you can see that every single electron is going to have its own unique force set of quantum numbers. So I'm going to quickly do the d here. If I have a d orbital, I've got 1, 2, 3, 4, 5. My n could be anything that I really want, except it could not be 2 or 1. Because remember that L has to be up to n minus 1. Okay? So if my n was equal to 2, 2 minus 1, the upper limit of L, would then be 2 minus 1 is equal to 1. And so if I have a 1, that means a p shell is the highest that I could have. But I'm saying here that I want to do a d shell. So what I would need, I'm going to erase that, what I would have to have is at least 3. And we know that's true because the lowest d shell is 3d. We don't have a 2d shell. Okay? And so then if we come here and we look at L, the L is going to be 2 if we're dealing with a d. Okay? And that is the upper limit because 3 minus 2, 3 minus 1 would be equal to 2 because it's n minus 1 is the upper limit. And so here I would have -2, -1, 0, 1, and 2. That's my range. And you can see each one of them represents one of the suborbitals. So let's say that I have an interest in the upspin electron in this second orbital. Well, then I would say m sub L is equal to, what would it be? 2, because I'm interested in this suborbital. And then m sub S would be equal to positive spin plus 1/2. So hopefully you guys are getting the idea of this. I can take any quantum number, principal quantum number to start out with, and then I have a variety of L's that I could obtain, which are going to tell me if I'm in the s, p, or d orbital. If I'm in an orbital higher than s, I'm going to have a variety of m sub L's to represent the suborbitals that I could be in. And then finally my spin, once I get narrowed down to a suborbital, is going to tell me if I'm interested in the electron that is spin up or spin down. So let's take a look here. I'm going to go ahead and work through this, but take a minute and pause the video and try to do this for yourself. Give the quantum numbers for the only valence p electron in aluminum. So go ahead and pause the video. I'll give you a second, and then unpause it when you're ready. Okay, so hopefully you were able to work through this, and we're going to go ahead and do the answers here. So if you take a look at your periodic table and you find where aluminum is, you see that it's in the third period. So the first thing you should have is n equals what? 3. Okay, so that's the first step. You want to make sure you have n equals 3. The next step is what type of orbital are we dealing with? So we know that we're in the third valence energy shell. What type of individual orbital are we dealing with? And that's our L number. Well, aluminum, we even said we want the only valence in the p shell. So if I'm in the p shell, L has to be equal to 1. So I know that my range of m sub L is going to potentially be -1, 0, and +1. And so when we're dealing with this, statistically you could find it in any of those suborbitals if you only have one electron. But if you are filling it up conventionally and putting the first electron in the first of those 3 orbitals, then we would say that you found an m sub L of -1. Again, 0 or 1 would be acceptable, but you have to pick one of them. And then m sub S is going to be equal to, you can have either plus 1/2, and conventionally we always write the electrons with a plus spin if they're unpaired, or it would still be acceptable to have a -1/2 spin. So that would be the answer for that one. Now here's another question. Explain why the following quantum numbers are not allowed. So again, take a minute, look it over, pause the video, and then restart when you're ready. Alright, so hopefully you guys were able to figure this out. If we come down to the first question, n equals 1 is allowable, but here's where I run into an issue. L has an upper limit of n minus 1. So if I put n in, 1 minus 1 means that 0 is the highest limit I could have for L. So what I'm saying is 1, I cannot have a p shell. There is no such thing as a 1p shell. There's only a 2p and above. So this has to be 1s, which means this L would need to be 0. Everything else in this entire set should be fine. So then if I come over here and I look at the next one, here I have n equals 3. That is plausible. L equals 2. That's fine. That would be the upper limit. If I took 3 minus 1, I would get 2. M sub L minus 1, that's within the range of negative 2 to positive 2, so that's fine. But I have a spin here of 0. I'm implying my electron would have no spin. That's not acceptable. Electrons have to have a plus 1/2 or a minus 1/2 spin. So that is the reason that that set of quantum numbers could not exist. So hopefully you guys found this useful. Thank you as always for watching. Please remember to like the video if it helped. Comment with any questions, concerns, compliments, anything you want if you have questions. And then go ahead and subscribe to the video if you would, because that is going to be the quickest way to find out when I release new material. So thanks a lot for watching, and I'll see you guys in the